Good morning all. Today I want to show off my new oscilloscope. It's the Keysight DSOX1102G. Now this scope has been very kindly supplied by Keysight Technologies, and it's one of their brand new 1000X series models, which was only released just a few days ago. So yes, this is a Keysight InfiniVision 1000X series oscilloscope with mega zoom technology. And you can see the strapline here, scrap the toys, get a real oscilloscope. And they point out that these scopes start at $449. Although if you want a G series model, then the first one is $649, and this one, which is the DSOX1102G, is actually $849. And the G series models have the integrated function generator and the frequency response analysis Bode plot facility. And I thought what I'd do today, let's switch the scope on, is take another look at this little filter circuit. This is an analog bandpass filter from the vocoder project. And I did a video on this a little while back. I'll put a little card thing up here, where I just fed some audio signals through here. And this is tuned to 1 kilohertz, and we heard sort of squealing noises. And it was all good fun, but it wasn't very scientific. So let's do something a bit more scientific today using the Keysight scope. So let's just remind ourselves what this circuit is. It's a dual op-amp. I think it's a 4th order bandpass filter, but I'm not sure whether it's Butterworth or what type of filter it is. The article doesn't actually say, but it's quite a tightly tuned filter. This one with these component values is tuned to around 1 kilohertz, so I'll be looking for a peak of bandpass response at that frequency. Now also from that magazine article there is a picture of filter frequency response curves, a graph I suppose it really is, and this is the frequency, this is the filter that I built. It's the 1 kilohertz frequency filter, so it's this one where they've drawn this curve in full, and you can see that it's quite a tightly tuned filter, but it also has this double top. It has 2 frequency peaks, and then it's tuned to sit so that the center frequency is in the middle of those 2 peaks. And I was just wondering whether I could see that on the oscilloscope. Now I'm going to need power for this little circuit, so I'm using this 12012 power supply which I built recently. It's got +12 ground and -12, so let's power that up with sort of 13.5 volts from my solar power system. So the op-amp is now powered, and the way I've got this set up is that I've got the wave generator output, the function generator output, going into the input of the op-amp circuit. Can't really see that at the moment, it's here, and the channel 1 scope probe is also connected to that input, and channel 2 scope probe is connected to the output of the filter. Now the filter's powered up, but of course it's not doing anything yet because there's no signal going into it. So let's switch on the wave generator, and that's given us, well, let's have a closer look. Now you can see that the wave generator settings are waveform sine. I think these are the defaults because I just pressed the default button. Frequency is 1 kilohertz, which happens to just coincide with the frequency response of the bandpass filter. So you can see that the output, which is the green trace, is actually very high here. The input is a bit low really, 500 millivolts peak to peak, so I'll nudge that up. In fact, I'll do that now. So I press that and then turn the knob. Let me just pull out of it so you can see the knob. So 500 millivolts peak to peak, let's up that. Let's take it up to, well, I think about 1.5 volts I can put in. 1.5 volts, and then the output is not clipped, so it's still within the rails of the op-amp. I could probably turn the output down a bit. Yes, that's fine. Frequency, as I say, 1 kilohertz. Now if I click that button, I can adjust the frequency in stages, and what I'm looking for is where the phase of the output signal is exactly in phase with the input signal, because that'll tell me where my resonant point is. But there's a bit of an issue here, and that is that below 1 kilohertz, the resolution of this dial, this control knob, is 10 hertz per click. Above 1 kilohertz, it's actually 100 hertz per click, so it's gone coarse above 1 kilohertz and fine below. And that's a bit of a nuisance, because my filter just happens to be exactly 1 kilohertz, and that's just at the point where the scope changes resolution. Now you can press that button and go to fine. Below 1 kilohertz, it goes in 0.1 hertz steps, so it is very fine. Above 1 kilohertz, it goes in 1 hertz step. So we've still got this problem of the discontinuity. But if I work around that problem, you can see if I get those two absolutely in phase, which is about there, that the resonant frequency of this filter is about 1.039, I suppose we could call it 1.04 kilohertz. Fantastic. Now, what about the double top of this frequency response curve? Now, the thing is, this is a Bode plot. So it's a plot of frequency versus amplitude. And we've got frequency in hertz here on a log scale and amplitude in decibels. Of course, what we've got on the scope is totally different. We've got amplitude in volts. And this isn't frequency, this is just time. However, if you look at the tops of the output curve, the green curve, as I bring the frequency down, you can see that they rise up. So that's one peak. Let's take it back to the resonant frequency of 1.04. Now I'll take the frequency up, and you can see that they rise up again. So either side of the resonant frequency, there's actually a lift. That's the low end. I've still got this problem that I'm jumping either side of the resolution of this control, so it's slightly awkward to do. But there's a lift below the resonant frequency, and there's another lift above the resonant frequency. Cool. Now I've gone back to the coarse control because it's fine enough below 1 kilohertz, but then it's far too coarse above 1 kilohertz. And I was thinking yesterday when I was playing with this, oh, I'll just cheat. I'll just build a completely different filter circuit that isn't centered around 1 kilohertz. But then I thought, well, no, that's not really the point. My filter is centered around 1 kilohertz. So how do I get around this issue of being coarse above 1 kilohertz and fine below it? And there is a way. Now, I should say something. If you've noticed that the output and the input, for that matter, are a bit jittery, well, yes, they are. And if I open this out, you can see why. There's a lot of digital noise on here. Now, let's see if we can get roughly at the frequency of the digital noise. It's about twice that, isn't it? These peaks, is that about it? 10 microseconds per division, and we're getting them a little bit more than each division. So 10 microseconds is 100 kilohertz. They're actually in between peaks as well, so it's probably more like 200 or 300 kilohertz. And of course, that's the frequency that my switch mode power supply is operating at to provide plus and minus 12 volts. So that switch mode power supply is rather noisy. Right, let's go back to this wave generator, and down here there's a button called settings, so let's press that. And there's a thing here, modulation, and I thought, if I could frequency modulate this so that the frequency gradually moves either side of my nominal frequency, and we have frequency modulation, there it is, then I could watch the effect of the frequency passing either side of the resonant frequency and watch the effect on amplitude of the output. So what I really want is a frequency modulation speed which is very, very low. So let's bring that down. That's that control there. In fact, I'm going to bring it all the way down to 1 hertz. Now, it would be quite nice if this went a teeny bit lower than 1 hertz, but it doesn't. And 1 hertz is fine, actually. So let's switch on the modulation. And now you can see that we're modulating the frequency of the input, and you can see that the output, the green curve, has these sort of burst jumps, but this is way too much deviation, so I need to take that down. We're currently set to 960 Hertz deviation, and what I want is, well, let's say about 100 Hertz, so that's there. So we're deviating 100 Hertz either side of the center frequency, which I'll need to go back to see, 960 Hertz. And clearly you can see that that isn't the center frequency, because at the low frequency where the input curve, the yellow curve, is widely spaced, this drops down suddenly. It doesn't drop down suddenly at the other end. So I want to center that. So that's not quite centered. It's now dropping down at the higher frequency. So I think I'll now need to go to fine control and try and get this drop off in amplitude to be equal either side of the center frequency. Now I think we had it at 1.040, didn't we? So let's go back to that. And I think you can see it there. It's doing a double bounce. So as the input frequency moves either side of the resonant frequency of the filter, the amplitude is doing a double bounce. Let's take the deviation up ever so slightly. Where is it? Settings, modulation, deviation. Yeah, that's the one that's currently selected. So let's go up to 120 Hertz. And that shows a little better. You can see the bounce either side of the center frequency. Let's go back to that. Tweak that center frequency ever so slightly. It seems to be dropping off more at the low end than the high end, so we're probably a bit low. That looks about balanced, but you can definitely see that double top. So this is a really amazing waveform generator. Not only can you specify sine, square, triangle. Let's just take a look at the options there. We've got sine, square, ramp, pulse, DC, noise. You can also switch on this modulation, and again the modulation waveform can be sine, square or ramp. So it's a really well specified wave generator. Now what if we could somehow store or get this trace to be persistent on the screen? Well, I've given the game away there. What I really want here is persistence. So I'm going to hit the display button, and here's persistence. Let's turn it on. Let's turn it on with variable persistence. I've set a time constant of 5 seconds, so these dots decay away in 5 seconds. And now you can see that that trace is actually tracing out this double top. So that looks a bit like this. I've got the double top of my number 7 curve here being traced out by the output. Now this isn't a frequency plot, but what we've got here is as the frequency of the input changes, and you can see the yellow curve expanding and contracting, the phase angle of the output changes. So as the frequency is low, the phase angle, the output actually leads. Does it lead? Where's the crossing point? There's the crossing point. Yeah, I suppose it leads the input. As the frequency becomes higher, so that the curve tightens up, then the output lags the input. So we're getting a movement of the output based on the frequency of the input. So it's a little bit of a cheat. It's not a true frequency plot, but we are getting that double top shape. Now there's a potentiometer on this filter circuit. Let me get the circuit diagram. It's here. It's the potentiometer, preset potentiometer to ground right at the beginning of the first stage. So I was wondering, if I adjusted that slightly, how would that affect both the frequency response of this bandpass filter and that double top, or the Q, I suppose, the quality factor of the filter. So I'm just going to nudge that potentiometer clockwise. Now what will that do? That will actually reduce the value of that resistor, and let's see what the effect is on the scope. Well, we're still getting this double top, but you can see that although I'm fully tracing out the first peak, I'm not fully tracing out the second peak. It's only going part way up into there. So what's happened is the center frequency, the resonant frequency of this filter has changed, and I need to adjust the frequency. So let's put it on frequency fine. Let's bring that down. Is that right? No, that's the wrong way. Let's take that up. Yeah, so it's a higher frequency, 1.07 kilohertz, and now I'm not seeing the full drop-off either side. I can see the two peaks there, but I'm not seeing the drop-offs beyond that. So what I really want to do is broaden the deviation. So let's go into settings, modulation, deviation, and let's take that up to, oh, that's quite coarse, 150 hertz. Let's come back and look at this one. Yeah, so I'm seeing it beyond the first peak. I'm not seeing it beyond the second peak though, so let's go up a bit higher. Let's take that up to 200 hertz. Right, now I'm seeing both the peaks being traced out. And they are further apart, so what seems to have happened is that the Q factor of the filter, or at least the top of the filter, has broadened out. We've got a more accentuated double peak, but the frequency of the filter, if I go back, has changed. It's now at a higher frequency. Right, let's see what happens if I turn the pot the other way. It was at exactly the midpoint, so I'm going to go that way a bit. Let's see what that does. Right, well, I clearly got a lot more gain because the output, the green, is actually off the scale. So let's drop that back. Wait for that persistence to fade away, which it has. And now I can see it sweeping through that band pass point, but I'm not actually seeing a double top there. The modulation is probably a little bit high. The deviation is probably a little bit high. So let's bring that back down. Let's try 120 hertz. I'm obviously off center now on the frequency, so let's go back and adjust the frequency. Right, so I'm sweeping either side of the resonant frequency, but I'm not really seeing a double top. So what seems to have happened by taking the pot anti-clockwise is that the filter frequency has narrowed, but I'm only getting one peak. So I'm just going to return that pot to its mid position, which seems to give a good compromise between the double peak, and you can just about see the double peak there. I'm off the frequency center again now, so this is going to be higher at about, yeah, so there's the peak. Let's just bring up the amplitude of the green channel so that we can see that, and I think that's really cool. So by frequency modulating the sine wave that's being fed into this filter, we've been able to see this sort of characteristic curve, this double top curve of this very tight bandpass filter, and I think that's just pretty amazing. Now I should point out that this particular oscilloscope does have a frequency response analysis system. If I press analysis, here it is, features of the FRA, the frequency response analysis. Let's turn that on, and we've actually now got a graph of frequency. Currently this is set to 100 hertz up to 1 kilohertz versus gain in decibels, and that is exactly what this graph is. So can I use this to plot the frequency response of this filter? Well, let's give it a try. So in setup, I want to set the minimum and maximum frequencies. Now I'm centered on 1 kilohertz. I don't really want the minimum frequency at, I want to press that button, don't I, to change it. I don't really want the minimum frequency at 100 hertz. However, this seems to be a very coarse control, and there doesn't seem to be a fine option by pressing the button. So I can either start at 100 hertz, 1 kilohertz, or 10 kilohertz. And that's slightly awkward, so I'm going to have to start below the center frequency, so start at 100 hertz. The maximum frequency really can't be 1 kilohertz because that's not beyond my frequency, the filter frequency, so that really needs to go up to 10 kilohertz. And this really is rather too large a range. Amplitude 1.5 volts peak to peak is fine. So let's go back and run the analysis and see what it does. Now, it seems to auto-gain the inputs and outputs. So it's varying the frequency of the input, the yellow, and it's watching the gain of the output, which is the green, and that rises up and falls back down again as it uses each different frequency. But now it's starting to see all that digital noise. So it's a bit of a mess. It does give me the curve that I want to see. In other words, it starts at 100 Hertz. The gain rises up to a peak of plus 20 dBs at 1 kilohertz and then falls away again towards 10 kilohertz. But this doesn't have the resolution I need to see that double top. Now, if I could perhaps in setup start this at 1 kilohertz and finish it at 10 kilohertz, then that would be a narrower range and I might just about see that double top. But of course then I'd have to change the filter so it wasn't centered around 1 kilohertz. I haven't yet worked out whether it's possible to adjust these starting and ending points with sort of finer granularity. Now, once you've run your frequency response analysis, you can move the markers here to different points. Notice also the pink curve is a phase angle, so you can see that ahead of the resonant frequency, the phase is a number of degrees above 0. At the resonant frequency, it should be at 0, which is that point there. Beyond the resonant frequency, it drops down to a lagging phase. What happens here, I'm not quite sure. I'm not sure whether that's actually genuine data. So the curve, pink curve, should come across, drop down at the resonant frequency, and then stay phase lagged. I think what this is seeing is all the digital noise. So you can pretty much ignore the phase output beyond this point here. But here are the results. At 1 kilohertz we have plus 18 dBs. At 1.259 kilohertz, the spacings are rather strange. It'd be quite nice if in setup you could set the actual step frequency rather than it pick its own step frequencies. But yeah, so we're down to 8 dBs. At this point we're at minus 6 dBs. Just down here there's one here which happens to be very close to 0 dBs, just off the center frequency of 1 kilohertz. We're at 1.97 decibels. But even without using the built-in frequency response analysis and just using the built-in wave generator, yes, you can get a sort of poor man's crude frequency response analysis in real time by watching the scope sweep the function generator either side of the filter's resonant frequency. So that was my first play with the Keysight DSOX1102G oscilloscope. That was just one evening's playing around with it, and I did focus mostly on the waveform generator, so I think I understand the waveform generator reasonably well. I mean, as well as frequency modulation, you've got amplitude modulation and all sorts of other ways that you can use this waveform generator. It's really fully spec'd. And the whole scope, I mean, there's so much more for me to learn. Like the mega zoom thing, you just press this zoom button and you can watch in zoomed version a little window of the trace up here, so you can watch the full trace and the zoom section at the same time. I mean, it's just so cool, and I've just got so much to learn. But yeah, I mean, this scope will pop up now and again in videos where I need a little bit more of a rigorous analysis that the little cheap kit scopes can't do, or I can't do with something like a DVM. So I just want to say a big thanks again to Keysight Technologies for sending in this oscilloscope. I'm happy. I've characterized my bandpass filter frequency. I think this is going to be a lot of fun. Cheerio.